started. As a reminder, your group for the mini project is due exactly in a week, so next Monday, right before midnight. How many of you don't have a group and are looking for other folks to form a group? Just one? All right, all of you guys just after class go over there, right next to that door, and then you can just talk among yourselves and try to figure out a group, okay? Or you can use Piazza to kind of look for group members. The locations of the TA office hours have changed, so by default they'll be in the Salvador Lounge, which is the lounge on the second floor of Davis Hall. Who here does not know where Salvador Lounge is?
Is that the big one?
Yeah, so that's the big lounge that's overlooking the Grace Plaza on the second floor. Okay. There are some exceptions, so please do look up the post or look up the syllabus for the details. Just in case, there were a few submissions we saw where it was not clear that the student quite understood what the homework policies was regarding sources and collaboration. So just as a reminder, there are only 5 allowed sources, and you can only collaborate with at most 2 other people on question 2 and 3. You're not allowed to collaborate at all on question 1. Okay? If for whatever reason this was not clear, it was confusing, you didn't follow the theme, you can withdraw your homework 1 submission by sending me email till Friday. If any of those things remain after Friday, all the academic integrity stuff will go into effect. Okay? So, yeah. Any questions on this? Any confusion? Angus? No. So Angus questions, can you only pick 1 out of 5? No, any of the 5, but nothing out of the 5 is allowed.
So you can use up to all 5?
You can use up to all 5, that's fine.
Okay.
And please make sure when you're writing a source, it's not something as vague as web, because that's clearly if we just take it at face value, that's not an allowed source. Okay, so please be as specific as you can. If you can, it's fine to just even put in the URL that you're using. That way, there is no ambiguity. But even saying things like, support page on this and things like that is enough. Okay. Any other questions? Alright, so we were looking to analyze, just about starting to analyze the runtime of the Gale-Shapley algorithm. Just as a reminder, here's the algorithm again. You have n men and women, each have a preference list. Guys, can I have your attention please? If you have to talk about something, you can just leave the room and talk outside. Okay? So initially, all men and women are free. And you run this loop till there exists a free woman who has not proposed to all men. So let W be such a woman, and let M be the best man that she has not proposed to. W proposes to M, and then if M is free, M and W get engaged. If M is engaged to some other woman W prime, then M gets engaged to the better of W and W prime according to his preference list. And finally output the set of engaged pairs as the final output. So even before we analyze the runtime of this algorithm, there are many data structure related questions that we have not talked about at all. And so here are 5 that we'll consider. The first is, how do you represent the input? Right? Because the input representation can make a difference to how fast your things can run. Then if you note the first line of the loop says find a free woman. So how do you find a free woman among all the free women? So how do you, for example, keep track of free women, and how do you get hold of one? And then once you have this free woman W, you have to quickly figure out who is the best man M that she has not proposed to yet. Okay. Once W proposes to M, you have to figure out who M is engaged to, or if he is free. If he is engaged to W prime, given M, W prime, and W, how do you quickly figure out if M prefers W prime to W or not? Right, so if you answer all of these questions, then you will finish implementing your algorithm, and then we also can do the runtime analysis. So it turns out that we'll have to talk about data structures to answer basically all questions. Question 0 is more of how you represent the input, but it's from 1 to 4 that will really determine the runtime of the algorithm. And so whenever you use a data structure, you have to initialize your data structure. Okay. Here's one common mistake: is students assuming that you can initialize an array of length n and initialize to a particular value in constant time. That's not true. Okay, it's not even true on actual systems, right? You can allocate memory to say from location I to I plus n. That's okay, but if you insist that the ith place has a certain value, you have to explicitly initialize it. Okay, so that's why if you try to allocate memory where everything is initialized to 0, that's much slower than just figuring out the memory locations for an array. Are there any questions on that comment? All right, so that's a general rule, whenever you have a data structure, you always have to initialize it. So that will contribute to the runtime. And we argued you have at most n squared iterations of the loop. And in each iteration of the loop, you're going to query each of the data structures and potentially even modify them. And so the question is, how quickly can you do that? Evan.
So, like when you initialize the data structures, where are you getting the information to initialize the data structures?
Evan's question is, when you're initializing a data structure, where are you getting the information for how to initialize it?
Like what to throw in there?
So Evan's question is, what should go in the initialize? That depends on your algorithm.
I guess based on the problem definition, right? Or the problem you're given, like the preferences. How do you then build that into a data structure without already being there?
So are you asking about the input or the data structure? Because they're two different things. Okay, so for your data structure that your algorithm uses, there's nothing that follows from the problem statement. It has to completely depend on your algorithm.
Okay.
Right? The question about input is, so we'll specify that. So in general, for any problem that you're solving on a homework, you will be given what the input is. And typically, we'll tell you what is the data structure. You can assume it's already given to you. If it's not, any reasonable thing is okay. So if, for example, if you have n items, assuming that it's given to you in an array is a reasonable assumption.
And you have to take into account the time that it took to initialize it.
So Evan's question is, do you have to take the time into account and initialize the input? No. So you always assume the algorithm is given the input to you in certain data structures. Now, of course, again, you have to be careful. I mean, you can't make ridiculous assumptions on what the input data structure is, right? So if instead of having everything input in an array, you assume it's sorted into the array, that's probably not a valid assumption. So you have to then include the time to sort, right? So, but things like assuming that they're given in a certain order, or they're actually in an array or a list, these are all reasonable things to assume. Does that answer your question? Any other questions? Any question on what Evan was asking in the first place itself? Was that discussion clear? Or? Everyone's good? All right. So I know some of you get bored in class. If you do, here's one puzzle that you can solve. Try to argue. So we've argued that the Gale-Shapley algorithm takes n squared iterations to solve the stable matching problem, but it can prove something much, much stronger. Any deterministic algorithm whatsoever cannot solve the problem in better than n squared time. But again, only think about this if you're getting bored. We have other stuff to do. So Any questions on what we're trying to do? Next. All right. So we're going to make a simple change to one of the notations we have been following, mainly because it just makes all the expressions that we're going to encounter much simpler. So we're going to assume that the set of men, instead of being m1 up to mn, is just the set 1 through n. And this square bracket notation, if you have not seen before, is just the set of integers from 1 to n. Okay. And similarly, we assume that the set of women is n. So what does this mean? If I have an index from n, now what I'm talking about is the mth guy, okay, the mth man. Okay. So this refers to the mth man. So what we're basically saying here is, instead of having this set m1 up to mn, I'm just indexing them by their indices. Okay, so I'm just moving that from 1 to n. Also, I'm going to assume that the array indices start from 1. All right. Oh boy. Can you guys see this? Is this okay? Or? All right, kind of looks weird from here, but all right. Any questions on these assumptions? All right, so the first question, or the zeroth question we want to answer is, how is the input represented? And so, I mean, there are a fair number of reasonable answers here. We'll just go with the one that's in the book, is that we'll assume everything is given to us in two-dimensional arrays. Okay. The two arrays are called man pref and woman pref to denote the preferences for men and women respectively. And if I look at the mith entry of man pref, okay, and this is the ID of the ith most preferred woman for M. Okay. So now what we are saying is, if you look at, it's a 2D array, you can think of, say, if it is a matrix or 2D array, then each row corresponds to a man M. And if you look at the ith entry of the row corresponding to M, that's his ith most preferred woman. So in other words, starting from index 0 to 1, it's like most preferred to least preferred. And similarly, you have woman pref wi, which is the ID of the ith most preferred man for W. Okay. And again, coming back to one of Evan's question, we always assume that the input data structures come preloaded with the input. So there's no initialization happening here. So when we query this data structure, we'll typically look at value of a specific entry. So say I want to know the ID of the ith mode, say the 100th most preferred woman for M, then I'm going to query manpref M100. And so if I have a two-dimensional array and I want to query a specific index, how much time would that take? How many of you know what I mean when I say a 2D array? Okay, so just to be sure, what I'm saying is you can think of this as a matrix, or so where each row is indexed by M, and you have n entries, and the ith entry in this case is manpref mi. And typically the way you represent this in practice is just you flatten it up into one large array. So if I'm trying to access a specific entry in an array, how much time would it take? Can someone speak up loudly? It's not. Sorry, I forgot your name. Alex. O of 1, right? So you're just looking up one location in memory, so O of 1. Good. And it turns out that in our implementation of the algorithm, we'll never modify this input ever. Right? So there is no update necessary. Okay, so this was kind of simple. So let's go to the next one, which is a bit more interesting. So the question is, how do we find a free woman? So again, remember, the set of free women at any point of time is a dynamic set. It can change depending on how the algorithm is going. So what would be the best way to keep track of this dynamic set of free women? What data structure would you use? Sorry? Boolean? No, data structure, Boolean. What data structure would you use to keep track? What you are saying, I think, is you have a Boolean array which says free or not, right? Yeah, but remember, if it's an array, then you have to move things around. It could work. Mark?
Yeah, use a
Linked list. So I was not just saying dynamic set just for the fun of it. It's like that's supposed to be the hint, right? So again, remember, if you have a dynamic set of items to take care of, linked list is the way to go. If it's fixed, then array is the way to go. All right. So we're going to maintain a linked list. Let's call it free. Of free woman. So if I'm maintaining a linked list of free women, how should I initialize the data structure? Remember, initially all men and women have to be free. Evan? Right, so you have to add in all the n women. Okay? So you add in all n women to free, and as we reviewed last time, adding each entry in a linked list is constant time. You're doing it n times, so this overall is O of n. Okay, then we have to query. So the query part is, in every iteration we have to figure out one free woman. Right? And as I mentioned before, from the purposes of the output of the Gale-Shapley algorithm, it really doesn't matter which free woman is picked as long as any one is picked. Okay? And so since we have everything in a linked list, the easiest way to pick one entry from a linked list is either from the front or the back, because it's like a constant time operation. Okay? So let's say, and again, you can do it from the back too. So let's say pick say first entry in free. And we'll see shortly why this is useful. Not only will we pick the first entry, we'll also delete it. So we're deleting the first entry from the linked list. So how much time would it take to kind of delete the first entry and read that first entry from linked list? O of 1, right? Because, okay, good. Then we want to update this list, and what do we have to do over here? We have to see, so let's assume somehow the algorithm figure out who is W's best unproposed man, let that be M, and let W propose to M. And at the end we have to figure out which woman is free and which woman is not. Okay? If we look at the statement of the algorithm, the main observation is if W proposes to M, the status of W might change, and the status of woman that W is currently engaged to might change. Other than that, nothing else changes. Right? So it's a very local change. Okay. So case 1, M was free. In this case, you do nothing, and this is where, and the reason you don't do anything is because you've already deleted W from the list of free women. Right? So if M gets engaged to W, W is no longer free, and all you had to do was remove W from the list of free women. Case 2, let's say M was engaged. So the second thing is M was actually engaged to W prime. In this case, M has to figure out who he prefers. So one case is if M actually prefers W prime to W. So if M, W prime remain engaged. So again, here's the deal. We took the free woman W out of the free list, deleted her from the free list. And now once we have finished the iteration of the algorithm, we discovered that M remains engaged to W prime and W prime remains free. So how should we update the free linked list? Sorry, I forgot your name. Ryan.
Put W back on free.
Yeah, so since W is now free, we have to put her back into the list. So as Ryan said, we'll just add W to linked list. And again, it doesn't matter whether I put her in the front or the back, both of them are constant time. Okay. Case 2.2 is if M now is engaged to W, that has to mean that W prime is now free. So we should add W prime to the free linked list. Add W prime to free. So how much would the total update time be? Someone other than Evan? I forgot your name, sorry. Brian.
Well, is there a pointer to the end of this?
Yeah, so you can assume you have pointed to both end and back. O of 1, right? So we're either deleting, let's say, to make our life simple, let's just say we delete from the front and we add to the front. Okay, so add front. Okay, so, and that's it. So we have figured out a data structure that keeps track of free women. We see that to initialize it takes O of n time, which is within the O of n squared time that we want overall to use up in the initialization step. And we have seen we can update and query this data structure in constant time. Right? Any questions on this? Okay, let's move on to the next part. All right, so the next question we wanted to answer was, so remember, by answering question 1, we know how to pick a free woman W. So now we have to figure out who her best unproposed man was. So how do we figure out who W's best unproposed man is? And so let me give you the answer to the data structure. We're just going to maintain an array of next. Okay, so maintain array next such that next of W is rank of man M that W should propose to next. Any question on the data structure? So it's an array of length n, and for at any point of time, if you look up next of W, that would give you the rank of the man M that W should propose to next. Okay. So again, we have to figure out the initialization. We have to figure out the query time. So who should W propose to? So remember, here I'm saying it's the rank, but what I really want an answer to this question is what is the ID M of the man that W should propose to? And then again, we have to update this. So talk to your friends for half a minute, figure out the answers to these questions. Like how would you initialize, how would you query, how would you update, and what would be the runtime for each of these operations? Are there any questions? Richard.
What does the S and T after next mean?
I'm sorry?
What does the S and T after next mean?
Oh, so Richard's question was what is this guy? This is the short for such that. Sorry. Any other questions? Okay, if not, how are you going to initialize this array? You guys are talking about the party of the class or what? Any suggestions? I have to ask your name. Jared. So Jared was saying you just put in the ID of the most preferred man for each next of W. It's almost right, except note by definition I want the rank. So I don't want the ID. So what would be the rank for each next of W? 1. Right? So you want the rank, most preferred rank is 1. Right? So the initialize is fairly simple. So you have next of W is equal to 1 for all women W. And so you're initializing n entries in an array. So this is O of n. All right, so next query, how would you figure out the ID of the man that W should propose to next? Evan?
You would then look at that, and then you can see like the data one look up on the original preferences.
Right, so the point is next of W gives you the rank, right? But the actual ID, if you replace I by the rank, you will get the ID of the man that W should propose to next. Okay? So all you have to do is look up woman pref W, and the second entry would be next of W. Okay? So what I'm doing here is I'm doing 2 lookups. First I have to look up next of W, and once I have next of W, I go look up the corresponding location in woman pref. So this is O of 1 time. All right. So once the iteration is done, and let's say W has made proposal to M, how should next of W change at the end of the iteration? Again, remember it's the rank. So if you just propose to next of W, what is the next rank? Ryan. Right, so rank side is the next guy, so the rank would increase by 1. So all you have to do is just increment the next value. Okay. So you just have to increment it. Okay. And again, it's just an increment, so what this means is you have to go look up a value in a location, increase the value by 1 and write it back. Right, so 3 operations, all of which are constant time. So O of 1. So in particular, like with our solution for question 1, we initialize in O of n time, and we can do both query and update in constant time. Okay? So again, we are going good. We want initialization to be no worse than O of n squared, and query and update time to be constant. Right? So we are maintaining that. Okay, good. So let's go to question 3. So now we are at a stage where we know the free woman W who should propose to, we know that she should propose to M. So we have to now figure out who is M engaged to. So how do we find out who M is engaged to? And in this case, we're going to do something simple. Since you have to just figure out one value for each man, just maintain it as an array. Okay, so we're going to maintain an array where at any point of time, if you look at the location for M, you're going to get the ID of the woman that he's engaged to. So in particular, let's call this array current. Okay. And in particular, if M is not engaged to anyone that is free, we're going to denote that by -1. Okay. You can pick any number that's not between 1 and n. I just pick -1. Okay. So current of M is -1 if M is free. Otherwise, it's W if M, W are engaged. All right, so again, we have to go through the initialization. And in this case, remember, everyone to begin with is free, right? So what we have to do is write current of M is equal to -1 for all men. And again, as before, since I'm initializing n entries, this is order of n. If you want to query, that is, want to figure out who is M engaged to, all we have to do is just go read the corresponding entry. Okay, so we just have to read current of M. So this is constant time. An update is just we have to go and update the current M value to whoever is his engaged partner. So if you remember, currently the situation is W is proposing to M. M is engaged to current M. Okay. So for update, what you have to look at is if M, W get engaged. So in other words, he was engaged to some other woman W prime, but now he is engaged to W. In this case, you just have to set current of M equal to W. Otherwise, that means if W proposed to M, but he does not accept W's proposal, then nothing changes. So he was engaged to W prime, he remains engaged to W prime. So this is no change. So again, this is just looking at the if statement and just either updating the value or not. And so again, this is constant time. So again, we have kind of the same kind of runtime guarantees. Initialization is O of n, query and update is O of 1. Okay. So if you remember, there were 4 questions. We are almost done. We need to figure out the last part. And this is where things get slightly more interesting. Okay. So the 4th question we want to answer is, given W and W prime, we need to quickly figure out who is higher in M's preference list. Okay. So you want to figure out if W is more preferred than W prime than not in M's preference list. So let's look at one answer which will try to just solve the problem without creating any other new data structure. So again, what do we have? We have the preference list for M in man pref of M. We have 2 women W and W prime, and we have to figure out which one is more preferred. Right? So remember, man pref is ordered by rank, so the most preferred comes before. So the simplest solution is just walk through the preference list of M and see which of W or W prime comes first. Okay. So so scan man pref of M and check if W prime comes before W. Now this is a perfectly valid and correct way to solve the problem, but do any of you see any issues with respect to runtime? Again, remember, this is a query that we want to make, right? So you're given W, W prime, and M, and we want to figure out if W prime is higher in the preference list than W. And so I gave you an algorithm that correctly solves this query. Alex.
It's over in time. That's bad.
Right. So the problem is, since you're doing a linear scan, in the worst case, you might have to go through the entire list. Right. So that's in worst case O of n or omega n. And that's bad because we wanted to get this query done in constant time. Okay. All right. Good. So The issue is O of n time, which will lead to an overall O of n cubed time, which is fine, but not the best we can do. Okay? So what I want you guys to do, talk to your friends for a minute or 2 minutes. Let me know if you have any questions. If not, think of a way to construct a brand new data structure that will allow you to solve this query in constant time. Any questions so far? Is everyone happy the way we have solved question 0 to question 3 so far? Richard?
What is 0 over those?
I'm sorry, where is that?
It's under engaged.
Sorry, I can't hear you.
Also, on the line with the update, if MW get engaged, under that line, there's a 0 over W.
Oh, so the question is, sorry, the acronym O/W, it's otherwise. Sorry, I forgot your name, even this told me like 5 minutes ago. Brian. So Brian's question is, at this point, can we claim that the algorithm is over NQ time? Yes, we can. Well, so you cannot claim without answering question 4 that it's O of n cubed time, because you have to argue that it can be solved in O of n cubed time. But you're right, all the data structures that we decided till before question 4, if we just froze the data structures there, then all the initialization steps is O of n time. It's just that the query time for this part 4 becomes O of n, and there are n squared iterations, so that's why you get n cubed. So n squared plus n cubed, O of n cubed. So you definitely have O of n cubed at this point of time. But we can actually do O of n squared, so that's what we want to go next. Matt?
Well, you can talk about processing a male preference list so that instead of the index referring to like their nth preference for the person, the index refers to how they prefer woman n.
Right, so if you look at what is the issue here, the issue is, if you look at the man pref, it's just giving everything is ordered in terms of rank, right? So first rank woman, the ID of the first rank woman comes in first, second rank comes in second, so on and so forth. If all we could do was switch the order, right? So if instead of having a list that ranks the woman ID by the rank, if we have another list for the preference list that the array is in order of the ID of the woman, but then it tells you the actual rank, then you can just go look up the entry for W and W prime and check whose rank is smaller. Okay, so that's what we're going to do, and this falls under the general category of what I like to call stitch in time saves 9 principle for data structures, which is many times it is useful to pay a fair bit on initializations up front because it will help you later on. Right? So remember, currently we could have used up to O of n time for initialization, but we only O of n squared, but we only spend O of n time. Right? So the idea now is we'll spend O of n squared time building up a data structure that will help us do query and update in O of 1 time. Okay? So the idea is build a data structure E of O of n squared time. So the query update for 4 actually turns out to be constant time. And the actual data structure they did, as Matt suggested, is just kind of flip this or whether currently the preference lists are indexed by rank. We want to come up with another version of the preference list just that is indexed by the ID. Okay. So here's what we want to do. So this is our final answer. We'll create a 2D array that we'll call ranking, rank, such that rank of m comma w is the rank of w in the preference list of m. And so we have to figure out how to do this initialization, but that's not too hard because we'll just walk through the man pref array and initialize this rank array. So what do we have to do? So the initialization, you go through all men, okay, and then you go through all possible locations in man pref, or j from 1 to n. And now you know the ID of the jth most preferred woman for m. So what you do is the rank for m's preference list for the jth most preferred woman in m's preference list is j. So you just kind of walk through the entire man pref list, and this way you can initialize the entire rank thing. Okay? And this is O of n squared because you have 2 nested loops, each running for n time, and you're only doing constant amount of work in each loop. Okay? So what do we do in query? We just have to check whether the rank of w prime is smaller than the rank of w, and again this is simply constant time because you're reading 2 numbers and comparing them. And we never have to update this ranking because the preferences don't change. So what do we have overall? So if you look at the total initialization steps, the first 3 initialization steps were O of n time, except this last guy comes in at O of n squared, which is fine because again we ultimately wanted O of n squared. And the query updates time from 1 to 4 is all the 4 guys we can do in constant time. So that's O of 1. So that implies overall we have the total time to initialize all the data structures, plus we have n squared iterations, and each iteration we have to do some initialize and update. So query update 1 to 4. So this is O of n squared plus n squared times constant, and so that's O of n squared. And that's it. So we have argued that the Gale-Shapley algorithm can be implemented over O of n squared. The important point to note that this is a linear time algorithm because the input size is 2n squared. Okay? All right, sorry for going over a bit. I'll see you guys on Wednesday.